To speak here. So I'm going to talk about single particle quantum mechanics and try to give an overview of some results involving correlation functions of the spectral measure for these operators, and in some way try to survey the state of the field at the moment. So I'll be talking about correlation functions for random Schrodinger operators. And I first want to give the general description. The models and the results vary a little bit between so-called lattice models that I'm sure you've heard about. So lattice models, these are models with the Hilbert space L2 of ZD, and so-called continuum models where we'll be working on L2 of RD. And unfortunately, there's not a complete symmetry in results concerning these. Primarily, the kinetic energy operator is usually a bounded operator in the lattice case and is an unbounded operator in the continuum model. And that is some source of some of the problems. And as we'll see, the theory of finite rank perturbations is very helpful in the lattice models and doesn't have a direct counterpart in the continuum models. So the Hamiltonians that I'll be working with always have the canonical form of H0 plus V omega, where V omega is the random potential. And the models that I'll be using are very simple. I'll describe them in detail. H0, one should think of as the background unperturbed operator. And so in general, that would have the form of L plus, let's say, some other background potential V0, might model the media in which the particle is propagating before you add impurities that give rise to the random potential. So L is going to be the Laplacian, either the discrete finite difference centered Laplacian on the lattice or the usual Laplacian in RD, and V0 is just some other bounded real valued potential. And this operator H0, the only requirement that I'm going to have on it, which I'll say, is that V0 and consequently H0 is, let's say, ZD periodic. So that's ideal for describing electrons in a crystal, which is one of the motivations of this model. Now, the random potential V omega, there is a canonical model for the random potential. Well, in fact, there are two or three usual ones. I'll be speaking about the so-called Anderson model, I guess appropriate at this workshop celebrating the 50 years of Anderson's seminal publication. There are also some results, especially spectral results, for the so-called Poisson model that I won't talk about here. So the Anderson model, so this is just a multiplicative self-adjoint operator. I'll assume that it's bounded. And it'll just be constructed in the following usual way. It's a sum over all lattice points, that is, points in ZD for either model, either in the continuum or on the lattice. And there's a family of random variables omega j, and they should be viewed as random coupling constants. So you have the random media as coupling to the electron through a what we'll call a single site potential u. That's a fixed function. It'll be localized at the point j. And u will always be assumed here, let's say, to be non-negative and compactly supported. So u is in L0 of infinity and real valued. So it's real. And then the family omega j, in some situations, we need very little requirements on that. So I'll always assume that omega j is at least a bounded process, real valued process on ZD. So this is the typical Anderson model. And let's say with a probability measure m, the usual case, and in some situations I'll be able to just deal with this general real value bounded process, but the usual case, the omega j's are independent, identically distributed. And in fact, most of the results are known when the probability distribution of any one of these in the so-called IID case, when that probability distribution is given by a nice bounded density. So the simplest case where all the results hold true is in the situation where mu naught, the probability measure for, let's say, omega naught, is given by a density of omega, is given by some density H0 of omega d omega. And again, let me take that H0 has compact support. Okay, so those are the general models that I want to talk about. As is well known, going back to the 70s and work with Pasteur, is that these are ergodic models. So at least in the IID case, where the probability space is just the product measure and the product space of each individual variable, in this case, I have to assume some sort of ergodic action if I'm just working with a general measure. But ergodic models, so in those cases, if UA is the translation operator of x is equal to f of x minus a, then if I look at the action of this operator conjugating the Hamiltonian h omega UA inverse, this acts for a in ZD by just translating the variables omega j, at least in the IID case, or otherwise I assume that you have an ergodic action on the probability space in the more general setting. So that's the usual thing. And consequences of this are profound for spectral theory of the operator and for the correlation functions, which I'm going to speak about. I should have made a little bit more precise that I wrote down that U is a non-negative single site potential here in the continuum case. So it might, for example, look like a bump function. That's the strength, that's the potential that the environment interacts through the random coupling constants with the particle described by that Hamiltonian H0. In the lattice case, of course, this is not a function, but this is simply the projection onto the site j. So let's say delta j, onto the site j. Okay, so that's just simply a single site interaction at the site j and translations of those. Okay, so let me talk about what the correlation functions are in this situation. So the correlation functions are in fact defined sort of as averages of spectral moments and observables. So correlation functions of the spectral measure for h omega. So let me define, for example, rho sub omega of I to be equal to, in the weak sense, the integral over I of the limit, or let's say the limit as epsilon tends to 0, these Green's functions that we saw this morning of the imaginary part of h omega minus e minus I epsilon inverse dE. So just this integrated version, and I want to speak about the density. So by rho of e, rho omega of e, I will mean the density of this measure, of the measure, okay, of rho omega. And so to define the endpoint or a family of n correlation functions, with respect to some observables, let's suppose that I have a family, A sub j, a family of self-adjoint operators that are covariant. And I'll write down examples, self-adjoint operators, and they are covariant with respect to the action. Okay, and let's suppose that we have n of them. So I can write down an endpoint function for the spectral measures and for these covariant operators. And I will write it this way. So let me take the trace of chi0 and chi0. So that chi0 is going to localize me. I'll put this over here. This is going to be localized near 0. So it's just a point projection in the lattice case. Otherwise, it's just a cutoff function centered near the origin in the continuum case. And what I'd like to put in here are a family then of, I'll write the density for the, what I mean by the endpoint correlation function. So these are covariant operators, so they depend on the random family omega. And so I just write here a product of n of these things at different energies, a to omega, up to rho sub omega of en, a omega, and chi0. So I want to take the trace if that exists. So that's a density, formally a density that depends upon the observables, but in particular upon the n energies, and then take the expectation of this quantity. Okay, and that quantity, and I think I'll write it over here to leave it. So kn of E1 up to En is in fact the trace per unit volume, is another way of saying what this expression is. The trace per unit volume, so the expectation of the regular Hilbert space trace of chi0, rho omega of E1, and all the way up to, times A1 omega, all the way up to rho omega of En, An of omega chi0. So a shorthand notation that I'll occasionally use for this would just be tau, trace per unit volume, of these operators. And of course, we don't know if this exists. An omega chi0. And I guess what I'd like to do is to show at least the smallest moments, that is for 1 and 2. These have something to say about the properties almost surely of this random system. In particular, the higher order moments have something to say about the transport properties of the system, which is one of the things that one would like to learn about, as we heard this morning, and I'm sure people here discussed throughout the semester. So this is what I mean by the endpoint correlation function with respect to a family of observables that are covariant with respect to the ZD action. And so the question is, do these things exist? Okay, so if I take this model, can you prove that, for example, if you look at the measure that's associated with this, the random measure that's associated with this, that it has a density? And so that's one of the questions I'd like to address. Now, I think I'll put over here, just as a reminder, what these models are. So this is H0 plus V omega, and either on little L2 of ZD or L2 of RD. And then H0 can just be taken to be Laplacian. You put some periodic background operator in there if you'd like. And then finally, V omega in the Anderson model is the sum of omega j, U of x minus j. So U is non-negative for RD. It's just the projection, let's say J in the ZD case. And then finally the notation, so M is the probability measure for this family, omega J. And I'll refer to IID case. And separately, if I use the distribution for omega 0, that'll be H0, okay, later on. Okay, so what do we know about these things? And why might they be important for understanding transport properties of the system? So for these operators that I've written down, the question of localization, that is the absence of transport, is now fairly well established, at least with certain regimes of disorder. In fact, I haven't put a disorder parameter in here, but you could put a disorder parameter in here. But in higher dimensions, let's say near the band edges or at the bottom of the spectrum, localization is now fairly well understood, and there's no transport. And of course, in higher dimensions, the question, as we've heard this morning, is there any sort of transport, non-trivial transport for these operators? So the transport...
You have in mind you're taking epsilon to 0 after you take the expectations of the traces?
I'm going to take epsilon to 0, no, before, because these are going to be the densities of the measures. So what I'm going to deal with is to prove that the densities exist by studying the measure. So in other words, I'm going to consider integrating these over certain sets, right? And then seeing that those put properties on those measures so that the density exists.
So you're going to integrate over E.
Right. I'm going to integrate over all the E's.
Trace,
right.
And then,
right. Right. And if I can control
as long as you
that,
don't take a single point.
Right. Right. That's what I'm not going to control. So if I can control these, then I'm going to try to give statements about the existence of the densities for those measures. Right, so for example, the existence of the density of states, I'm going to look at the integrated density of states, control the integrated density of states, and then the density will exist by the Lebesgue differentiation theorem.
But you're taking an expectation before you take single points.
Yes, yes, yes. Taking the expectation is going to be critical. Right. Okay. So the transport properties. Right. Well, yeah. I haven't written. I'm just trying to give the heuristics of the theory. So the transport properties are controlled by these moments, k sub n. And I should say that at least what I learned about these at Pasteur in early articles in the 70s and early 80s was a person who advocated the use of, or looking at these and trying to understand whether or not these measures have densities associated with them. So we're going to look at some questions of existence of the densities associated with these measures. with measures. Okay, so that's the first thing. So, well, why don't I start off with the simplest and perhaps the best studied situation is when n is equal to 1, so we only have one spectral density that occurs here. And also let's take the simplest case where the observable, covariant observable, is equal to the identity. Then it's easily recognized from this formula, the expectation of the trace, then of chi 0, spectral density E omega, rho omega of E, chi 0. Well, this in literature, of course, is the density of states, n sub n of E. So this is the density of states for the model. Okay, and this has been studied in the lattice case in the 80s. So let me look at the lattice case ZD. Wegener gave some estimates on the existence and basically proved that the density of states for this model exists on the lattice and is bounded function. In fact, we heard some of this morning. There's a bounded function on the spectrum of the operator, the set that exists almost surely. Okay. The existence of the density of states in the situation that I discussed for the continuum model, well, there are various versions. A lot of people worked on it. But in a very general setting, in joint work with Jean-Michel Combe and Frédéric Klopp, we have results on the existence of the density of states as a bounded function. So in the other case, I wanted to say a few words about that. This follows from, well, also in the lattice case, a so-called Wegener estimate, okay, which was first introduced in Wegener's paper in 1982 for the so-called, for the finite volume Hamiltonians. So all of these correlation measures that I've introduced can, in fact, instead of using the trace per unit volume type of formulation here, can also be defined by taking a system, putting it in a box, renormalizing, and then taking the limit as the size of the box goes to infinity, particularly well known for the n equal to 1 case. So if I denote by h lambda simply our family h omega restricted to a volume lambda, so this is a finite volume, let's say a box in either case, and it puts some self-adjoint boundary conditions, let's say since everything's periodic, boundary conditions. And then take the usual eigenvalue counting function. Of course, for each fixed omega, this is just a nice self-adjoint operator, periodic boundary condition, so it has a discrete spectrum. The eigenvalues are, of course, random variables. But if I take the usual eigenvalue counting function, n sub lambda for the volume lambda as a function of E, simply be the number of eigenvalues of h lambda, and put an omega there to remind you that that is, in fact, a random matrix. Eigenvalues of h lambda omega less than or equal to E. And then rescale this appropriately, dividing by lambda, then I can ask about the existence of this quantity. So I can take the limit as lambda goes to infinity in volume of n sub lambda of E divided by the volume lambda. And this was limit, when it exists, would be the integrated density of states. And so now this quantity for the models in general, let's say the IID case, this exists for almost every energy. And that has been well studied. And that will be the density function, the distribution function, sorry, for the density in n equal to 1 case. And so what one tries to do is to study the behavior of capital N of E and extract from that enough boundedness in order to prove the existence of little n of E and to show that it's locally bounded in energy. Okay, so one wants to study, so n of E is the distribution function of little n of E. Okay, and now what one tries to do is to get good estimates in the volume on the number of eigenvalues less than or equal to E. And these types of estimates do go by the name of Wegener estimate. And then one obtains, as I'll show, information about the integrated density of states in this particular situation. So what we need to do is, let me give an example in the RD case of work due to myself with Combe and Frederic Klopp in a rather general setting. So let me take the situation where the omega j are in fact simply distributed by a probability measure with a probability measure m and are bounded. And bounded random variables, not necessarily ID. So in the most general setting, what one does is consider mu j to be the probability measure of the jth variable conditioned on all the other ones. So this is the probability measure, the conditional probability measure of omega j conditioned on the other ones, on omega k for k not equal to j. And then what we do is define a so-called Levy concentration function, which is associated with this process. And the Levy concentration so the Levy concentration is defined the following way. So I will call it S of epsilon. And so what we do is we look at the measure of intervals about an energy E of size epsilon. So this is a conditional probability distribution for omega j, and that's the weight given to this interval E to E plus epsilon. Take the supremum over all energies E in R, and then take the supremum of this over all lattice sites in ZD. So this is a concentration function for this particular measure, which I started out with M. And it turns out that this is a very nice, this controls the integrated density of states defined over here.
You take the supremum of the conditions?
So I take the supremum, I take supremum over E, I take supremum over all the sites. Omega j is simply the measure, let's say, of this interval conditioned on all the other ones.
Do you take the supremum of the condition?
What's that? Yeah, that's in the definition of mu j. Mu j is the conditional probability measure.
We take the supremum over the condition.
Conditional probability depends on the values elsewhere.
Yeah, so I take...
He's asking if you're taking
Yeah.
a soup over
Yes,
the
I am.
values elsewhere.
Yes. Yeah, sorry if it wasn't clear. Right. Okay, so what I want to say is then the following result in this general setting. Is that, so then as a theorem on this, so under the conditions, if I take any compact interval, then the following is true. There exists a constant Ci, a non-negative constant C sub I, such that at all energies E in this interval I, and for all epsilons bigger than 0 and small, then if I look at the density of states at E plus epsilon minus the density of states at E, this is a monotone increasing function, so this of course is non-negative, and it's bounded below by this constant times this Levy concentration at value epsilon. Okay, so this is a general result about the behavior of integrated density of states under these conditions. And of course, I assume that it exists. It's not necessarily true under a general probability measure that it exists, but I'll assume that we have conditions so that n actually exists. It's bounded above. Now, this would be of interest in controlling the density of states, provided you know that this concentration S of epsilon goes to 0 as epsilon goes to 0. It need not we need not control this S of epsilon in general. But as an example, if we take the IID case with the density, then that immediately implies that the so-called integrated density of states, the IDS, is Lipschitz continuous. If you have weaker information. If you only have, let's say in the IID case, that the probability measure is Holder continuous, then you get that the integrated density of states is Holder continuous with Holder exponent alpha. So that gives some regularity properties, at least on the integrated density of states. And in this nice situation, it immediately gives the result that is, in fact, for RD, that you have information about enough control, Lipschitz continuity, to show that this is differentiable almost everywhere, and that derivative is, in fact, the density of states. So this also implies that N of E exists. Now, one of the open questions here is, what about regularity in both the lattice and the continuum case? And there's not very much known beyond what I've already summarized here, and I'll say a few more words about this. Not too much is known, especially in the continuum case, especially in the RD case. Okay, and we'll see that coming back again. Now, let me, let's see, I think what I'd like to do, let me just say a little bit about this finite volume estimate and the Wegener estimate, because it plays such a key role in these correlation functions and also in properties of Anderson localization for the spectral properties of these systems. So for this, I go back to the finite volume situation. So let me go back and talk about this Wegener estimate. So you look at our finite volume Hamiltonian H lambda of omega, and here what one wants to do is consider the spectral family. So these are just the sum of spectral projectors that take out the eigenvalues in the interval that I put in here. So this is the spectral family. And a typical Wegener estimate is for the following. It's an estimate on the trace, that is the number of eigenvalues, so the trace of this spectral projector for an interval I, and then you take the expectation of that. And a good bound above on this would be the following. In the general case stated in this theorem, this is bounded above by a constant, let me call C Wegener, and then this Levy concentration function at 2 epsilon, and then times the volume. So in the IID case, what we have is an upper bound, which is a constant, times the volume, times, in fact, the length of the interval. So here I should say where the interval has length epsilon. Okay? So this type of finite volume estimate has played a very, very important role over the years in Anderson localization. In addition to controlling the integrated density of states for this model. And the proof for this estimate generally has 2 steps, which I just mentioned because they're of somewhat independent. Well, it has the proof of the estimate over here, the main theorem, has 2 steps. One is the estimate for the finite volume Wegener estimate. The second main step is so-called spectral averaging. And the spectral averaging estimate is used in order to take advantage of the expectation there and regularize the situation. So let me come back to that one. Let me just say a word about what spectral averaging is. It has several other applications in this field. So what is the spectral averaging situation? Well, in general, let me take an example. Suppose I simply look at a 1-parameter family of operators, let's say h sub lambda, which is some h0 plus lambda v. So it's just some 1-parameter family. And spectral averaging in the simplest form says the following. You look at the resolvent of this 1-parameter family at energy E minus I epsilon in the beginning, and I look at the weighted matrix element between the square roots of V. So you use V as a weight. So let me, for simplicity, assume that V is a non-negative, can be an operator, need not just be a multiplicative operator. So one wants to average this over lambda. So the basic spectral averaging result is that if I take some probability density and I integrate, let's say from 0 to 1, this quantity over lambda, then it's bounded above by a constant depending upon V times the norm of phi, let's say, squared, where this is independent of epsilon. So this is the most primitive spectral averaging result. Goes back in version to Kotani-Simon and Kotani's trick. And we use a more generalized version of this in order to prove the theorem. But I want to give an idea of what's involved there. Let's see, the last thing I want to say about n equal to 1 are a few words about other regularity results, because there are some things known. In the lattice case, just summarize two of them, in ZD. So a result which, in fact, I'll mention in relation to proofs of higher order correlation functions a little bit later, goes back to Konstantinescu, Froelich, and Spencer, an old result, CFS. And so in this situation, what they studied is, suppose that we're in the IID case, all right, that I have on the left there, and that H0 extends to a strip in the energy plane. So suppose this extends to an analytic function to, let's say, absolute value of energy less than R. So suppose that you have good control. For example, suppose it's a Gaussian distribution. So you have an extension there. Then, in fact, at high energy, the density of its states itself, little n of V, has an extension to a strip in the energy plane. So then, for high energy, n of V extends. So outside of some interval about, let's say, 0 energy, n of V extends to an analytic function in a strip. Extends analytically to a strip. Okay, so that's one known high energy result. And the other result which I'd like to mention is due to Bouvier, Compagnano, Klein, and Perez, which has a slightly weaker assumption on the probability density. So they have a family of results that say that if the probability density has some sort of regularity, then the density of states has some sort of regularity, and they are related. So for example, if h of t, h naught of t is, I should call it h of t, is the characteristic function of h naught, so the characteristic function of the probability measure, let's say, mu naught. And then suppose you have something like 1 plus t to the power k dimension plus k times h of t belongs to L1. So suppose that you have enough control over h of t, the characteristic function of the single site probability measure, up to amount k, so dimension plus k, then this implies that n of e is smooth, so C infinity of k plus 1, I believe, k plus 1 on R. Provided, though, that you have large disorder. Large disorder. So those are some either high energy or large disorder results on the density of states. And I guess I'd like to mention, so in general in the continuum models, very little, if anything, is known about regularity of the density of states, aside from its existence, which I already mentioned. There is this intriguing question that Tom Spencer mentioned this morning in his talk, is suppose that you look, so here's an open problem, quite related to ideas being discussed here. So suppose you put in a coupling constant, so h omega of a lambda is equal to h0 plus a lambda v omega, and then look at the behavior of the density of states as lambda goes to 0. Okay, in any of these cases, and study, see what happens for various energy regimes. So look at n sub lambda of E as lambda tends towards 0, and see what happens there. So let me move on and talk a bit about the second moment situation. Here it's known that the density of states does not have information about the transport properties of the system per se. And so if one goes to higher moments, one might be able to extract information, and that's what I'd like to try to show you. So let's go to the situation where n is equal to 2. And now for my covariant operators, I'm going to take the velocity operators. So a sub 1 of omega will be equal to I'll just take the case where the same. So I take the commutator of the position operator, let's say the alpha component of the position operator, and this is a deterministic operator, so this is V alpha. And because this is a simple quantum mechanical calculator, of course, the potential commutes with multiplication by x alpha, so this is deterministic independent of omega. And in this case, our second moment, K2 of E1, E2, and let me put in velocity. I can put in two components. Let me take the positive measure, which is the same velocity operator, same component of the velocity operator, V omega, then that becomes equal to the expectation of the trace of chi 0, the spectral projector for, let me write it as DE1, V alpha, DE2, just using this notation for a density. Then I have to put, I should put over here, sorry. Put this the same, so DE1, DE2. So this is going to be for the operator, and then chi 0. So I put the expectation of the trace of that. And so this is the second order moment. It's called the current correlation measure. So for example, if I take two intervals, let's say delta 1, delta 2 in R, then I want to consider m alpha of delta 1, delta 2, just the integrated version of this. This would be the expectation of the trace of chi 0. The spectral projector for delta 1 and omega, V alpha, spectral projector for delta 2, V alpha, chi 0. Okay, so that's a way of writing the integrated version. And one wants to study the properties of this particular measure. So in the diagonal case where both components are the same, this is in fact a positive, corresponds to, one can prove there exists a positive measure. A positive measure on R2. And then the question is, does there exist a density for this measure? And why is a density in this case particularly important? Because I want to show you that it corresponds via the Kubo formula to the DC conductivity for this one particle model. So let me give a rough idea of that. If you use the relaxation or the linear response approximation as computed by many people, so let me say the linear response theory. Okay, then that gives us a formula for Kubo's formula for, let's say, the DC conductivity. So this is the DC conductivity, 0 temperature, T is equal to 0, and the Fermi energy, EF, is given. And so there's a nice way of expressing that in terms of the Fermi projectors. So this is the limit as epsilon goes to 0 of the integral of the characteristic function on the interval up to the Fermi energy, E1, minus the characteristic function up to the Fermi energy at energy E2, divided by the difference of the energies, E1 minus E2, and then times a cutoff delta function, approximate delta function, depending upon parameter epsilon, and then times, in fact, this particular measure. Okay, so this would be, let me write it as m alpha, and so this would be the alpha component of DE1, DE2. So it's this measure which arises, especially in linear response theory, in the Kubo formula for the DC conductivity. So clearly understanding that measure can be quite helpful. If you make the heuristic assumption, in fact, that that measure has a density, then one can carry out the integration in the Kubo formula and get a nice heuristic formula for the DC conductivity. So if cap m alpha of dE1, dE2 has a density, little m alpha, E1, E2, dE1, dE2, then in fact, carrying out the integration, you find that the DC conductivity for the alpha direction at Fermi energy EF is nothing more, DC, is nothing more than the diagonal component of this density m alpha EF, EF. Okay? So it seems to be somewhat important to understand the behavior of this measure as follows from the Kubo formula. And so let me give you a picture maybe of what's going on. So here I consider my two energies, E1 and E2. So this is R2, the energy plane. Of course, the diagonal is where the action is according to this formula. So if you understand the behavior as you approach the diagonal, let's say at the Fermi energy, then the value of this m alpha is in fact, so if this is our Fermi energy for the system, then the value is in fact the DC conductivity. So clearly, what you have are the following properties. So in the localization regime, for this random system, so if EF falls in the localization regime, then you know from various results that the DC conductivity should be 0. And of course, one of the large open questions here, one way to rephrase the transport regime is that if EF is in some transport regime, then, or equivalently, I should say, the m alpha at EF should be positive, okay, bounded below by some constant. So that is certainly one of the main open questions about random Schrodinger operators phrased from another point of view, trying to get those properties. So a little bit of information has been gained about the behavior of this current-current correlation function, although there is still a lot unknown in the existence of the density. With Jean Bélissard, we studied this in the strong disorder regime, and in fact what we showed in the lattice case is that if you look away from the diagonal, of course, all the action is taking place near the diagonal, but if you look outside of the diagonal in a small strip dependent upon the disorder, then in fact this density exists, m alpha of E1, E2, and in fact is a real analytic function. So away from where all the interesting information is, the density exists as a real analytic function. That was work with Jean Bélissard. So in the lattice case, away from E1 equal to E2 in large disorder, so basically the system is in a localized state, large disorder, then m alpha E1, E2 exists and is real analytic. Okay, but it doesn't tell us very much about the conductivity. And I just want to mention, though, that the method of proof goes back to the idea that I said before about the Konstantinescu-Froelich-Spencer, where one uses the fact that you have a nice path expansion for the resolvent in order to prove this result. And that's the same sort of idea. The same method can be applied to higher order, applies to higher order Kn also. And in fact, applied to higher order Kn is written over here. What one shows is that away from the coincident planes where Ei is equal to Ej, then these densities exist and are also real analytic functions. But in some sense, that of course is only a first step because that's away from the diagonal. Now with Jean-Michel Combe and Francois Germinet, we try to study a little bit the behavior on the diagonal. And what we have are just some preliminary results. So in the free case, then M of E1, E2, you can compute it, and it has a delta singularity. So there's a real singularity on the diagonal in the free case. And so what we showed is that if you take an energy EF in the localization regime, that you have better control in the localization regime. Of course, we know that in that regime, the DC conductivity is 0 by many authors who have looked at that. But we wanted to study exactly what was the behavior going to the diagonal. So let me finish my...
Peter, could I ask you, in the work you did with Belisar, you need to have large disorder if you're away from the diagonal or not?
Yeah, a large disorder, yes.
Even
Yes,
if
it's
you're
a
away from
perturbative.
that-
It's
even
still a
if you're away from
perturbative.
the diagonal.
Yeah, well, we still did. Yeah, it's a perturbative expansion, so to control the convergence.
But
Yeah.
you know it exists away from the diagonal,
Yeah.
right?
Yeah, it exists, and well, we proved it's real analytic.
Oh, no,
Yeah.
I realize that you need
Right.
to be away from the high disorder, but you can prove that it makes sense, and you can get bounds away from
Away from the diagonal,
Diagonal?
for fixed lambda or for
yeah, for fixed lambda.
for fixed lambda. I don't know. I would look at that. Right, that might be improvement. Right. Probably, well, we could discuss probably with your proof, probably not, or with that method of proof, probably not. But yeah, that's a good question. But so towards the diagonal, what we do is the following. So if we're in a localization regime, so let's suppose we're at the bottom, as this picture sort of illustrates, at the bottom of the spectrum. And let's suppose that here you're in some sort of localization region at the bottom of the spectrum. Let me just arbitrarily put it at 0. And so let's take a small, look at a small region about, so here I want to take EF, deep in the localization regime, and take a small box about that. So cut some box of size I epsilon. And so what we're able to show is the behavior of this current correlation measure. So I epsilon is a small interval, let's say, of size epsilon about EF in the localization regime. So I look at then the measure cap M alpha of I epsilon. And so what we're able to prove is that this is bounded above by epsilon cubed times log of epsilon to a power 1 over s times a constant s for all s bigger than 0 by some iteration. And so what this shows is that M, so this would imply then, because we have high enough power of epsilon, that M alpha at EF is finite, in fact, equal to 0. So reproving via the Kubo formula the fact that you have no DC conductivity in the strong localization regime, but we do it by getting some estimates, of course this is non-negative, some estimates from above on the rate of vanishing of this current correlation measure. And let me just conclude by saying this is strongly related, and somewhat of an open conjecture, it's strongly related to the Mott formula for the AC conductivity that was recently proved by Abel, Klein, Lenoble, and Mueller, to the Mott formula. So this is Klein, Lenoble, and Mueller. And what their formula suggests is the following, that the component, the density, if it exists, should behave like E1 minus E2 to the power 2. And then there's a logarithmic factor here, 1 over E1 minus E2, or absolute value of 1 over E1 minus E2 to a power, let's say, they have a power D plus 2. So the behavior of this is strongly related. If you look at the AC response of the system and look at the results on the Mott formula for the AC conductivity, then the vanishing on the diagonal should at least be E1 minus E2, and then they have an extra term that appears also in the Mott formula, which gives a mild type of logarithmic divergence here on the diagonal. And it's also related to localization length formulas. So this concludes. So the formula for the localization length also involves this current-current correlation measure. And so what is that? So for example, in the paper of Belisard, Van Enst, and Schultz-Valdez, you find the following formula that the localization length associated with an interval delta in energy, well, the definition of it is the following. It's through the moments of the position operator. So it's the limit as the time average capital T goes to infinity of this trace per unit volume of, let's say, the alpha component of the position that's been propagated by the Hamiltonian, e to the minus I h omega t x alpha e to the minus I plus I h omega t. So I look at the behavior of the position operator minus, let's say, some fixed point squared. So the second order, it's well known that this also was mentioned this morning, the mean displacement of the system projected onto an energy interval p delta. So if you look at this, take this as the definition of the square of the localization length for the system in an energy regime delta. So of course in the strong localization regime, this should be 0. So what one finds is that L squared of delta is equal to the integral, double integral over delta and over R of exactly this measure, m. So let's say I'm still using alpha component, so m alpha of dE1, dE2, and then it's singular on the diagonal as E1 minus E2 squared. So both by looking at the Kubo formula for the DC conductivity, or by looking in analogy with the Mott formula, or by looking at formula for the localization length, one can conjecture the behavior of this density as you approach the diagonal, that it should go as E1 minus E2 squared with some power of logarithm as you approach this diagonal. And that, of course, would give control on DC conductivity and the localization length. So I hope that, at least by presenting these examples, it gives some idea of why one would like to look at these moments. If you want to look at higher order moments, then in fact you can express the higher order moments of the position operator in terms of the k sub n's that I wrote down. So all of the transport properties of the system, at least if you define that by looking at expectations of position operators in higher moments, can be expressed in terms of these higher order correlation functions. And so some control of them, especially on these critical hyperplanes where the energies coincide, would give a lot of information. Just a last word, and I know there'll be talks by Jean-Michel Combe later on Friday. There are another family of second order correlations in the finite volume systems, which I just wanted to mention. They're a little bit different because they really are questions for finite dimensional systems. So finite volume second order correlations. So I'm speaking about so-called Minami estimates, which are of a little bit different type, but they are second order Minami estimates. So in his study of the local eigenvalue spacing for these random Schrodinger operators in the strong localization regime, he came upon a very beautiful estimate, which I can write down. So I recall that the Wegener estimate, we looked at the trace of the spectral projector for an interval I, and for the system in a box lambda. So lambda is a finite volume. And proved that this was bounded above by a constant times the volume times the length of the interval. So this is Wegener. Minami needed to look at the following type of correlated estimate, where he looks at the expectation of the trace of the projector squared minus itself. Okay, so it is involved a finite second moment, and prove this is bounded above by another constant times the volume squared times the length of the interval squared. And so he proved this for lattice models, and subsequently there were two other proofs of lattice models by Graf and Vaghi and by myself, Bailey-Sard, and Stoltz. And then there is a more recent proof due to Combe, Germanet, and Klein, which he'll discuss on Friday, of this in the lattice case, but also an extension to some energy intervals in the continuum case. So this is also, in some sense, a first start of looking at the behavior of the eigenvalues of the finite volume system themselves. I mean, it took many years to come up with another proof other than Minami's original proof. It took at least 10 years to do that. But one could also think of this as a start to look at other properties, in particular eigenvalue spacing properties of these finite volume systems, whereas most of what I talked about dealt with the infinite volume system to begin with. So I hope that gives a little bit of overview of some of the work on correlation functions for these random Schrodinger operators. Thank you.
Okay, Christian.
What should be the optimal estimate instead of epsilon q? Should it be epsilon to the 4 up there, over there?
Oh, for this?
Even up there, epsilon to the q.
Oh, should this be, this should probably be epsilon to the 4, but we can't prove it.
Where do you lose this power in the proof?
Because we only use some very crude sort of Holder type estimates coming from strong localization regime and the Wegener estimate. I mean, we still don't really use a strong sort of correlation type estimate in proving it. And so we have to iterate an estimate, and that's where the log S contribution comes from. So
Okay.
you bound...
Do you use Minami or you don't use Minami?
Let's see. In fact, the initial estimate does not use Minami. I was just trying to think. We had, I think, an unwritten estimate where we used Minami, but I'll have to check. I think if you can figure out a way to use Minami, you might be able to improve the epsilon power. I'll have to check. Right.
I'd remind you in one dimension for the actual original Anderson model, where H is characteristic function, one actually knows the density of states is C infinite.
Yeah,
So
thanks.
here's a challenge. Is that true or not true in higher dimension lattice model?
And the reward is?
What?
And the reward is? What should we give? A bottle of champagne? Of fame. So
That's
even in the
always the
Anderson
reward.
model. Okay. So, but this is sort of a subscript of your millennium problem, right? On continuity, the integrated density of states for general ergodic system.
No, the
You are-
millennium problem is a much weak. No.
Yeah, it's weaker.
That's a simpler.
Similar statement. Hard.
And that's actually for the continuum. So
Right.
that millennium problem is the discrete case is known
Yeah, it's known
and
as
is
discrete.
much simpler. No, this is a more subtle fact, but the fact that you actually expect smoothing,
Right.
not right.
True
So
that.
these results that say it's as smooth as.
Right.
Right? So
Yeah. No, I
any
completely
result
agree
that,
with you. Right.
that-
In some sense, the proof that I sort of sketched with Combe and Klopp.
Tell you what, you want to reward? Tom Spencer paid me 25 cents many years ago for proving the original result.
Okay.
I'll pay that 25.
Oh, there's inflation and everything, and this is a so it should be 25 pence. 25 pence plus inflation, right?
Plus inflation.
Yeah. Yeah, I do.
The problem is I invested that 25 cents, so it's now worth only 12 and a half.
I was going to say, actually, it's worth that much. I was going to say it's worthless. I should say, and Barry pointed out, that a lot of the 1D results I didn't mention, and not just for lack of time. There are a lot more things, such as that result is known in 1D. I was trying to concentrate on higher dimensional results. Thanks.
Okay, any other? Yes?
Well, physicists have studied also a lot level curvatures or level dynamics for studying localization properties of Anderson model. I mean, can similar analysis be carried for these quantities?
Well, let's see.
Derivatives with respect to boundary conditions.
So has it been done? I mean, you mean for the correlators, the higher order objects?
Yeah, you're mentioning different correlators that can be studied for.
Yeah, there's There's, I mean, what has been proven, I think, pretty much is what I sketched. Okay, now what we'd hope to prove is a lot more, including smoothness of the density of states. There's a nice paper by Kirsch, Lenoble, and Pasteur, for example, that discusses some of these issues from a very physical, heuristic point of view. There's a lot of insight. And there are some lectures by Pasteur on these sort of things. But what has been proven, I believe, more or less is what I described. We'd certainly like to prove a lot more.
I would just like to make a comment that one can study these systems, and you, I think, have given a very nice overview of what's known. If one looks at random band matrices,
Oh, well, thanks for
then
that.
things are much better. And it's a simpler, in many cases, a simpler problem, especially if you have Gaussian disorder.
Right.
So although we don't understand things like transport for that, the density
Right.
states is much better controlled, precisely because you have randomness everywhere, and not just not just on the diagonal, the off diagonal element. And this makes an enormous difference in terms of control of density of states and average Green's function. So we have much better control over those cases. But if you go away from Gaussian disorder, we'll hear, I think we'll hear today from Hislop that there are fine questions about density of states, even for random matrices, which are very tough, and many of them still wide open.
Yeah, well, your results with co-authors for the band matrix are on the semicircle law up to a certain approximation of the width of the band.
No, but
Maybe you have
we can get
additional-
smoothness of the density of states.
Right.
No problem, as long as
Well-
you're in the interior of the spectrum,
Mhm.
and all questions related to Green's functions, as long as the energies, real parts of the energies are the same, and you're on the same side of the axis. You don't want to be on different sides of the axis,
Yeah.
then the problem becomes extremely complicated. But I'm just saying, it's in general a simpler question than because of the presence of more disorder.
Simpler is,
Yeah.
it's still a challenging problem, right?
Okay. Any more questions?